Firstly, let me explain the motivations for the study of this topic. Yeah. So there are mainly two motivations. The first one is construction of manifolds. So basically, it is a hard problem to construct a new example of complex manifold. But there are some known examples which are obtained by taking symplectic resolution over singular varieties. That's symplectic varieties. So this is one motivation. And the other is generation of symplectic manifolds. So, for example, if we consider a singular case surface with AD singularity, so they can be regarded as a multi-generation of a visual case surface, and such singular case surface is given a point. So, on the boundary of module space of so case surface, so from this point, the generation of compact manifold is also interesting topic. But today in this talk, we concentrate on this first motivation. So as I said, constructing a new example of symplectic manifold is basically a difficult problem, and there are only a few examples are known, so when we talk about classification of complex manifold, we usually consider irreducible homomorphic manifold. Ancient short. So by definition, this is that symplectic homomorphic symplectic manifold with a symplectic homomega, but that exceeds empirical complexity, and the space of two forms on X is generated by the symplectic form. So in general, for every complex manifold, if we take finite metal cover, then it is decomposed into a product of IHS and complex tori. So
X is scalar?
Yes, 1 minute, yeah, we can projective or scalar. Yeah, so in this topic, we only consider projective variety, so we change project. So there are only few types known up to deformations. The first example is the Hilbert scheme of points. on a K surface. The second is so-called generalized Kummas. Generalized Kumma varieties. So this is also obtained from considering the small points on a surface, but here we consider Argonian surface instead of a PC surface. And the Hilbert scheme itself is a symplectic manifold, but it is not simply connected, so we should take some appropriate subvariety. Then we get this IHS generalized Kumma. And there are also exceptional examples due to probability. They are often called OG10 and OG6. These first two examples appear as a family, so for each end we have a defined deformation type of varieties, but this only gives two examples up to deformation. And then these are the motivating examples of this first motivation transaction. These are obtained by taking a symplectic resolution of certain singular module spaces. So next, we introduce the module space of sheaves on a surface. So here we consider a surface S, which is K3 surface or Argonian surface. And we also fix an ample divisor on S. And to consider modular space of sheaves, we fix some numerical invariant C. So this represents Chan classes. So this is the element of the cohomology ring of S. For each such C, there is fourth modular space MC SH. So this depends on parameters H and C. That's parameterized like this. Gizuka semi-stable sheaves. Such that chiffon S whose Chan classes equal to the fixed C. So I don't explain the definition of Gizuka semi-stability. So this depends on the choice of the ample divisor H, and so if we consider semi-stable sheaves instead of all sheaves, we get a projective modular space. So we can have a modular space has a certain projective scheme. So this modular space can be singular, and the smoothness can be determined from the choice of the parameters. So next we give a result about singularities of this modular space. So for the choice of the ample divisor, we assume that it is generic. So if we choose more special ample divisors, then the corresponding modular spaces tend to be more singular. So we choose H to be generic to get the modular space to be more as much smooth as possible. Then there are roughly 3 cases. The first case is when the numerical class C, this is the element of some convolution group. If this is primitive in this Abelian group, then the corresponding modular space is smooth and also symplectic. So this symplectic structure is due to Rak-Kyeong. So in this case, the modular space is smooth, and in fact, up to deformation, this is the same as the Hilbert scheme of points. So if the surface is Q3 and this becomes generalized Kumma, we take Abelian surface and also appropriate subvariety. In the second case, if C is twice of some primitive element, A prime, then in this case, the modular space is singular. In fact, it has a symplectic singularity, but this has a symplectic resolution. So in fact, this singularity is isomorphic to some important orbit closure in SP6, SP4, and so the resulting modular space, resulting resolution is in fact these two modular spaces, IHS. So yes, so in the case of KC surface, the resolution is OG10, and in the Abelian surface case, if we take some appropriate subvariety of the resolution, then we get OG6.
So your anchor line should be general.
Yeah, here you be asking about transmission. So if we take non-generic polarization, then the modular space gets more singular. And so even if this is primitive, this becomes singular, and in fact, the singularity is isomorphic to some fewer variety. And the final case, this is again non-primitive. We so similarly C prime is primitive and m is greater than 2. Then in this case, the module space is again singular, and also they don't have any symplectic resolution. They never have symplectic resolution. So this result is due to Harding, Ray, and Soga.
This is also for non-generic.
For these two,
The last one.
and the last one, yeah, so in all examples, which is changed, can
Non-generic case, can it's still true.
yeah, so even if we take special non-generic polarizations, yeah, this just becomes more singular than again never adults. So because of this result, we can't produce new examples of IHS as a module space. But we can still ask or propose the following problem or question. What find symplectic? So the module spaces. So
other condition C flat in the second
yeah,
dimension when C prime is
dimension of C prime.
2で割れるというだけで、C プライムに対するモジュラーの次元が決まってなくて。
Yeah. I mean, yeah, so the dimension should be some fixed. Yeah, so for higher dimensions, it's just absolute. For certain small dimensions. So we just consider this problem and so when the module space is smooth, so in the first case, there are many studies of finite symplectic actions on a smooth module space. And there are also examples of finite quotients of smooth module space that are with symplectic resolution. But they do not give new examples. And so we can also consider quotients of singular module spaces for the second and third cases. And the remaining time of these talks, yeah, I will give some very explicit example, finite quotient of singular module space. So actually, I'll consider involution or singular module space. Here, we consider a K surface. And so, there is a similar theory for urban surface, but for some technical reason, we only consider K surface. And we assume that the Picard group of S is generated by the amplitude divisor H. So in particular, this H is generic. And we also choose a specific chunk class. This is 306. And consider the corresponding modular space. So we simply write MC H. So in this case, this is a singularity, but because of this is in the third case, and this has dimension 20. The dimension can be computed from this numerical data, and we also consider the following bilateral involution. I from NC to NC defined by taking the dual of the sheaf. So the reason of the choice of this C is firstly, in order for this involution is to be well defined, the first chunk class must be 0, and also so for lower ranks, so this becomes identity for rank 1 and rank 2. But in rank 1 case, the module space parameter is ideal shift, so yeah, the taking there doesn't make sense. But for rank 2, so every locally free shift is atomic to its dual because of the vanishing of C1. So the rank 3 is the smallest non-trivial case. And we choose this C2 just because we want to make the dimension of the module space as small as possible. So this is the minimal possible dimension, but still this has dimension 20. Then, and I should say that this is not defined on the whole module space a priori because this parameterizes not only locally free shifts, this also parameterizes non-locally free torsion free shifts. So a priori this is not defined on the whole space, but we have the following result. So this involution, irrational involution, extends to this has the following three properties. The first three, this is to a biregular involution, and also this is non-trivial. Finally, this is a symplectic this preserves the symplectic form of the module space. So in the rank 3 case, this really gives a non-trivial example, non-trivial action. So I give a very rough sketch of proof of this proposition. So the final statement, the fact that I preserves the symplectic form is relatively so high. It just so this can be checked directly. So I want to skip the details. That's statement. So basically, the symplectic structure comes from the tangent space of the module space is isomorphic to self-extension of the sheaf, and the symplectic structure is obtained by the cup product of the x1. And by looking at the action of I on the tangent space, so we can directly check that this preserves the symplectic structure. And for the regularity of the inversion, we consider the following Donaldson Williamson compactification. So this module space has a birational morphism to another module space, so-called compactification. So I don't give a precise definition, but basically this is a module space parameterizing slope semi-stable shapes. So there's another notion of stability other than the Gizeh-Kassan stability. So then this module space is a space of sheaves modulo some weaker equivalent relation. So this is a bit small compared to MC. So this is in fact the birational morphism, and we consider the exceptional locus of this birational morphism. Then to show the biregularity, we use the following facts. Firstly, this phi is a divisorial production. And secondly, the rank of the Picard group of the module space is equal to 2. So this is the second one is just a consequence of the assumption that the Picard rank of S is 1. By combining these two facts, so we can show that this birational inversion preserves ample divisors. So the other consequence, we can say that I is biregular. So if the Picard rank is greater than Picard rank of S is greater than 1, so then the Picard rank of the module space also gets large and gets larger. And so in that case, usually if the Picard rank of the module space getting bigger, then it tends to have more and more birational models, and so in that case, probably this is not biregular, just birational. finally, for the non-triviality for the inversion, so we use the following two facts. The first one is for sheaves of the Miller space outside this special divider. So this is a single irreducible divisor. We have for sheaves outside E, it is isomorph. F is self-dual if and only if this cohomology group is non-zero. So the one direction is easy. So if F is self-dual, then this F-dual has a non-trivial homomorphism to F, so this gives a non-trivial element here. And conversely, for the converse, we need stability of F. So we can characterize the self-duality via this homology group. And also, for general shift inside E, we have a trivial homology group, just homology group for F tensile. So basically, it is hard to describe shifts outside E. So yeah, we have no idea about what shifts outside E look like. But for shifts inside E, it is relatively easy to describe the property of the shift. And in particular, we can show that for such shifts, F actually this is 0. So by the second statement, and by the semi-continuity, we can say that for sheaves on non-empty open subset of the modular space, we have this vanishing. So then this implies, by combining with the first statement, so we can conclude that I is not trivial. So in fact, at least for the case of K3 surface, so we can say more. So we can also say something about the fixed locus of time. But at least this argument shows that I is not trivial. So in this way, we have everywhere defined non-trivial symplectic involution on the modular space, singular modular space. And finally, I want to discuss the existence of a symplectic resolution of that modular, the quotient of a modular space. So around this exceptional divisor, this variation of phi is locally modeled by Weaver varieties. For the following Weaver Q. So this is a Weaver having two vertices and two loops on one vertex and two arrows in the different directions. And we also consider the dimension vector 3 and 6. Then, so in this case, the space of stability conditions is one-dimensional. So basically, essentially, there are three stability conditions: positive one and 0 and the negative one. And so and the bidirectional morphism phi is locally identified with a morphism between the Quiver varieties with the same delta phi. And but by definition, this image theta is defined as the hyperkähler quotient of the representation of this double quiver for the action of the product of GL3 and 6. So this is a double quiver, so the representation space has a natural symplectic structure. We can consider its hyperkähler quotient. And so the phi between the Mogen species is locally realized as a morphism between the Quiver varieties obtained by the variation of the stability parameters. So we also have the Mogen space corresponding to the negative stability condition, theta minus. And so in fact, also locally we have an involution, and that involution is regarded as an isomorphism between these two Mogen species. We can write this like tilde. But this diagram is not commutative, and the involution, like birational involution here, descends to a biregular involution on this affine Mogen space, affine Quiver variety, and this lifts to the regular involution on this Mogen space because of the various proportions. And in fact, this is a local picture of the Mogen space, but we also have a global, similar picture for the global Mogen space. So in that case, there is also another Mogen space, which is a Mogen space of certain stable objects in the derivative category of S. Anyway, so we have such a diagram, and so we have a regular involution on this Quiver variety. So then the question is, does theta plus or 0 in involution have a bit symplectic? I still don't have an answer to this question. So the original motivation for the study of the singular variety is the existence of the resolution. But in the case of K3 surface case, so in fact, globally we don't have a symplectic resolution. Whether or not this question is affirmative or not. So if in fact UNIST has isolated my fixed points. So basically, this is a picture around the exceptional divisor, but in fact, this module space has a isolated fixed point outside. So this particularly implies that the global module space does not admit a symplectic resolution. So this is the story for K3 surfaces. And for ordinary surfaces, the story is basically similar. So at least around E, the module space has the same singularity as the P variety. But outside E, the situation must be different compared to the K3 surface case. So if outside E there are no isolated or there are no fixed points with respect to I, then this becomes an important question. So if there are no isolated, there are no fixed point outside
So
E.
what proportion to K3?
Yeah, so this is only for K3. So for ordinary surface, there might be no fixed point outside A. And if this also admits a symplectic resolution, then globally this is symplectic resolution. And finally, I should remark that this is just a very specific. This is just one particular example of a finite symplectic quotient of a singular module space, and there should be many other examples. And yeah, it should be interesting to study such examples. I stop here. Thank you.